Hello everyone, welcome to the final video lesson for Chapter 3 of the Foundations of Scalable Systems. The components of distributed systems communicate over a network. In communications technology terminology, the shared local and wide area networks that our systems use to communicate are known as asynchronous networks. And the slide here shows the characteristics of asynchronous networks. Basically, nodes can choose to send data to one another at any time. The network is half duplex, meaning that one node sends and must wait for a response from the other. These are two separate communications. The time for data to be communicated across the network between nodes is variable due to reasons like network congestion, dynamic packet routing, and transient network connections failures. The receiving node may or may not be available when you send it a message. It may have crashed. Data can be lost. In wireless networks, packets can be corrupted and hence dropped due to weak signals or interference. And nodes do not have identical clocks, hence they are not synchronized. So what are the implications of asynchronous networks for our applications which communicate between nodes across an asynchronous network? Well, put simply, when a client sends a request to a server, how long does it wait for a response? If the client doesn't get a reply, what should it do? Let's explore these scenarios in detail on the next slide. The core problem here, namely whether a response is received, is known as handling partial failures, and the general situation is depicted on this slide. This slide depicts the possibilities when our clients and servers communicate. The first three basically are good outcomes. If I send a message to a server and I get a response very quickly, then I'm happy. And if I get an error very quickly because the destination IP address lookup fails or the node on the process on the server has failed, then I'm happy because I've got a failure and I can handle the error message accordingly. The last three are a little bit more complicated. The request is received by the target server, but it fails while processing the request and it never sends a response. What about if the request is received by the target server and it's really busy? It processes the request, but it takes a long time, maybe 37 seconds to respond. Or the request is received by the target server and the response is sent, but the response is never received by the client due to the network congestion and the packet being dropped. So if we get the result we want from the server, or we get an error message, then the client can proceed. Fast failures that can be detected quickly are easy for a client to deal with. It knows what the situation is. The other three pose a problem, however. They don't provide any insights into the reason why a response has not been received by the client. From the client's perspective, these three outcomes look exactly the same. The client just can't know without waiting, potentially for a long time, whether the response will arrive eventually or it'll never arrive. And waiting for really long times doesn't really get much work done in your software applications. So partial failures present a dilemma for a client, but actually there's a more insidious problem because the client cannot know if the operation succeeded, the server executed the business logic, updated the database, and then it tried to return the result and it didn't arrive because of a network or server failure. It just doesn't know if the request succeeded or not. The typical solution that clients adopt to handle these faults is to resend the request after a configured time period. However, this is fraught with danger, as the slide here illustrates. Basically, the client sends a request to the server to deposit money in a bank account. When it receives no response after a timeout period, it resends the request. Now, what is the resulting balance? The server may have applied the deposit or it may not the first time, depending on the partial failure scenario. The chance that the deposit may actually occur twice is a fine outcome for the customer, but the bank's unlikely to be amused by this. Therefore, we need a way to ensure in our server operation implementations that retried duplicate requests from clients only result in the request being applied once. This is necessary to maintain correct application semantics. So to ensure we implement our server operations correctly and updates are only applied once, even in the face of client retries, we need to have a property called idempotence. Idempotence operations can be applied multiple times without changing the result beyond the initial application. This means, for the example on the previous slide, the client can retry the deposit request as many times as it likes, and the account will only ever be increased by $100. Requests that make no persistent state changes are naturally idempotent. This means that all read requests are inherently safe and no extra work is needed on the server. Updates, however, are a different matter. The system needs to devise a mechanism such that duplicate client requests do not cause any state changes and can be detected and filtered out by the server. In API terms, these endpoints cause mutation of the server state and must therefore be idempotent. The general approach to building idempotent operations is outlined on the slide here. Clients include a unique idempotency key in all requests that mutate state. The key identifies a single operation from a specific client or event source. It's usually a composite of things such as a user ID, the session key, unique values such as a local timestamp, a UUID, or a sequence number. On the server side, when a server receives a request, it checks to see if it has previously seen the idempotency key value by reading from a database that is uniquely designed for implementing idempotence. If the key is not in the database, this is a new request. The server therefore performs the business logic to update the application state, and it stores the idempotency key in the database to indicate that the operation has been successfully applied. If the idempotency key is in the database, this indicates that this request is a retry from the client and hence should not be processed. In this case, the server returns a valid response for the operation so that hopefully the client won't retry it again. The data store for idempotency keys is usually implemented in a separate database table or a collection in the transactional database used for the application. It may also use a dedicated database that provides very low latency lookups, maybe such as a simple key value store. Unlike application data, idempotency keys don't need to be retained forever. Once a client receives an acknowledgement of the success of an individual operation, the idempotency key can be discarded. The simplest way to achieve this is to automatically remove idempotency keys from the store after a specific time period, such as 60 minutes or 24 hours, totally depending on your application needs and volume requests. Idempotence basically means an update is applied exactly once to some application state. Exactly once is an important notion in distributed systems. It doesn't mean that there are no message retransmissions and failures, retries and application crashes. These are all inevitable. The important thing though is that the request eventually succeeds and the result is always the same. We'll return to the issue of communication delivery guarantees in later lessons. As the slide illustrates here, there's a spectrum of semantics, each with different guarantees and performance characteristics. At most, once delivery is fast and unreliable. This is what UDP provides us. At least once delivery is the guarantee provided by TCP/IP, meaning duplicates are inevitable. Exactly once delivery, as we've discussed here, requires guarding against duplicates and hence trades off reliability against performance. Inevitable communication failures have another implication for the way that we build distributed systems. This is best illustrated by the two generals problem, which is depicted on the slide here. Imagine a city under siege by two armies. The armies lie on opposite sides of the city, and the terrain surrounding the city is difficult to travel through and visible to snipers in the city. In order to overwhelm the city, it's crucial that both armies attack at the same time. This will stretch the city's defences and make victory more likely for the attackers. If only one army attacks, then they're likely to be repelled. Given these constraints, how can the two generals reach agreement on the exact time to attack, such that the generals both know for certain that agreement has been reached? They both need certainty that the other army will attack at the agreed time, or there could potentially be disaster. To coordinate an attack, the first general sends some messengers to the other, with instructions to attack at a specific time. As the messenger may be captured or killed by snipers, the sending general cannot be certain the message has arrived unless they get an acknowledgement messenger back from the second general. Of course, the acknowledgement messenger may be captured or killed, so even if the original message does get through, the first general may never know. And even if the acknowledgement message arrives, how does the second general know this unless they get another acknowledgement from the first general? And so it goes. The two generals problem is analogous to two nodes in a distributed system wishing to reach agreement on some state, such as the value of a data item that can be updated at either. Partial failures are analogous to losing messages and acknowledgements. Messages may be lost or delayed for an indeterminate period of time, the characteristics of an asynchronous network as I described earlier in this lesson. In fact, it can be demonstrated that consensus on an asynchronous network is impossible to achieve within bounded time. This theoretical result is known as the Flp Impossibility Theorem. Luckily, FLP is a theoretical limitation, demonstrating it's not possible to guarantee consensus will be reached with unbounded message delays on an asynchronous network. In reality, distributed systems reach consensus all the time. This is possible because while our networks are asynchronous, we can establish sensible practical bounds on message delays and retry after a period of time. FLP is therefore a worst case scenario, and as such, I'll discuss algorithms that enable you to establish consensus in later lessons. Finally, in this lesson, let's look at the notion of time in distributed systems. Every node in a distributed system has its own internal clock. If all the clocks on every machine were perfectly synchronized, we could always simply compare the timestamps on events across nodes to determine the precise order in which they occurred. If this were reality, many of the problems I'll discuss with distributed systems would simply go away. Unfortunately, this just ain't the case. Clocks on individual nodes drift due to environmental conditions like changes in temperature or voltage. The amount of drift varies on every machine, but values such as 10 to 20 seconds are not uncommon in a day, or with my current coffee machine at home, about 5 minutes a day. If left unchecked, clock drift renders time on a node meaningless, like the time on my coffee machine if I don't correct it every few days. To address this problem, a number of time services exist. A time service represents an accurate time source such as a GPS or an atomic clock, which can be used to periodically reset the clock on a node to correct for drift on the network. The most commonly used time service is the Network Time Protocol, NTP, which provides a hierarchically organized collection of time servers spanning the globe. The root servers, of which there are 300 worldwide, are the most accurate. Time servers in the next level of the hierarchy, and there's approximately 20,000 of these, synchronize to within a few milliseconds of the root server periodically, and so on throughout the hierarchy, with a maximum of 15 levels. Globally, there are more than 175,000 NTP servers. Using NTP, a node in an application running an NTP client can synchronize to an NTP server. The time on the node is set by a UDP message exchange with one or more NTP servers. On a local area network, machines can synchronize to an NTP server within a small number of milliseconds accuracy. One interesting effect of NTP synchronization for our applications is that resetting the clock can actually move the local node time forward or backwards. This means that if our application is measuring the time taken for events to occur, it's possible that the end time of the event may be earlier than the start time if the NTP protocol has set the local time backwards. In fact, a compute node has two clocks. These are the time of day clock and the monotonic clock. The time of day clock represents the number of milliseconds since midnight, January the 1st, 1970. In Java, you can get the current time using the system.currentTime_milliseconds call. This is the clock that can be reset by NTP and hence may jump forward or backward if it's a long way ahead or behind NTP time. The monotonic clock represents the amount of time in seconds and nanoseconds since an unspecified point in the past, such as the last time the system was restarted. It will only ever move forward, however. It may not be totally accurate because it stalls during an event such as a virtual machine suspension. In Java, you get the current monotonic clock time using system.nanotime. Applications use NTP to ensure the clocks on every node in the system are closely synchronized. It's typical for an application to resynchronize clocks on anything from 1 hour to a 1-day basis. This ensures the clocks remain close in time. Still, if an application really needs to precisely know the order of events that occur on different nodes, clock drift is going to make this fraught with danger. There are other time services that provide higher accuracy than NTP. Crony supports the NTP protocol but provides a much higher accuracy and greater scalability than NTP. This is the reason it's been adopted by Facebook. Amazon has built the Amazon Time Service by installing GPS and atomic clocks in data centers. This service is available for free to all AWS customers. The takeaway from this discussion is that our applications cannot rely on timestamps of events on different nodes to represent the actual order of these events. Clock drift, even by a second or two, makes cross-node timestamp comparisons meaningless. The implications of this will become clear when we start to discuss distributed databases in detail. In summary, distributed systems are made up of multiple independent nodes that need to communicate and agree on system state. The lessons for this chapter have covered the basics of distributed communications, consensus, and time, all of which are fundamental constraints on the way we need to think about scaling our systems. Thanks for watching.